All right, so I'm live. Bismillah, alhamdulillah. Okay, let's read. Bismillah. Where is it gone? This one, this, this one. The path to Newton's second law. The formula F equals ma, which defines force as the product of mass and acceleration. So force equals mass times acceleration is one of the most pivotal concepts in classical mechanics. Known as Newton's second law of motion, it represents how force influences the motion of an object. Known as Newton's second law of motion, it represents how force influences the motion of an object, stating that the force acting on an object is equal to its mass multiplied by its acceleration. This seemingly simple equation has profound implications, as derivation stems from centuries of intellectual effort, from ancient Greece to the Islamic Golden Age, and ultimately to the groundbreaking work of Sir Isaac Newton in the 17th century, which is 1600s. Understanding F equals ma, force equals mass times acceleration. The equation, let's go here. Yeah, a bit better now. The equation F equals ma, or force equals mass times acceleration, explains how force, mass, and acceleration are related. In this formula, F stands for force, which is a push or pull acting on an object. M represents mass, the amount of matter in the object. A stands for acceleration, the rate of change of velocity of the object over time. The rate of change of velocity of the object over time. In essence, the formula means that the greater the force applied to an object, the more it accelerates, but the object's mass will resist this change in motion. For instance, pushing a light object results in a noticeable acceleration, while a heavy object with greater mass would accelerate less under the same force. Newton's derivation of the formula. Newton's second law was derived from a combination of his observations of the natural world and the work of predecessors. Newton built on Galileo's work on falling objects, which demonstrated that objects of different masses fall at the same rate, challenging previous assumptions. Galileo had already formulated the concept of uniform acceleration, and Newton extended these ideas by asking how forces cause changes in motion. Newton reasoned that for an object's velocity to change, a force must act upon it. This was in contrast to earlier beliefs, particularly those of Aristotle, who thought that force was required to maintain motion rather than just change it. So Newton reasoned that for an object's velocity to change, a force must act upon it. Otherwise, okay. Newton recognized that force was not directly linked to speed, but to the change in speed, acceleration. His insight then was that acceleration is directly proportional to the force applied to an object and inversely proportional to its mass. From this understanding, Newton derived the relationship F equals ma, force equals mass times acceleration, quantifying the interaction between force, mass, and acceleration. Historical origins of force and motion. Newton's derivation of the second law of motion was not developed in isolation. Centuries of scientific thought from ancient Greece and the Islamic Golden Age laid the foundation for his groundbreaking insights. In ancient Greece, Aristotle theorized that motion required continuous force. He believed that an object's natural state was to remain at rest and that any motion needed a constant push or pull to be sustained. While this idea shaped early science, it was incomplete as it failed to account for the role of inertia, an object's resistance to changes in motion. Okay, during the Islamic Golden Age, 8th to 14th century, scholars translated and critiqued Greek texts while contributing their own advancements. A significant figure was Ibn al-Haytham, whose work in optics and physics laid important groundwork. He questioned Aristotle's views, suggesting that an object in motion does not need continuous force to remain in motion, hinting at the concept of inertia. Later, figures like Ibn Sina refined these ideas. Ibn Sina proposed that force relates to an object's speed, an early precursor to understanding that force influences acceleration rather than velocity. Newton's breakthrough. By the 17th century, the intellectual advances of earlier scholars converged with Newton's genius. In his 1687 work, Philosophia Naturalis Principia Mathematica, I don't know how you pronounce it, Newton set forth his three laws of motion, with the second law providing a mathematical framework for understanding how forces affect motion. Newton's second law revolutionized mechanics by explaining that a force acting on an object causes it to accelerate, and this acceleration is directly proportional to the applied force and is inversely proportional to the object's mass. Newton also built on his first law of motion, the law of inertia, which states that an object will remain at rest or in uniform motion unless acted upon by a force. The second law, expressed as F equals ma, added precision to this by quantifying how force affects changes in motion. For instance, if a force is doubled, the acceleration is doubled, but if the mass is doubled, the acceleration is halved under the same force. Influence of the Islamic Golden Age. Professor Jonathan Lyons, a scholar of cultural knowledge, emphasizes in his book The House of Wisdom that Newton's achievements were deeply influenced by the intellectual contributions of Islamic scholars. Lyons argues that while Newton's synthesis of knowledge was extraordinary, it relied heavily on the preserved and enhanced knowledge passed on through Islamic scholars during the Golden Age. The critical translations of Greek texts and original contributions in areas such as optics, physics, and mathematics created the foundation upon which European science, including Newton's work, was built. Newton's lasting impact. Newton's formulation of force equals mass times acceleration represented a monumental shift in scientific thinking. Before Newton, motion was not understood with the clarity and precision that the second law provided. His work unified centuries of disparate ideas into a coherent theory that applied universally, from the smallest objects on Earth to the motion of celestial bodies. This law allows scientists to calculate forces in a range of physical systems and remains fundamental to our understanding of the physical world. In conclusion, the second law of motion, embodied in the formula F equals ma, was not solely the product of Newton's genius, but the result of centuries of intellectual development, from the speculative ideas of Aristotle to the breakthroughs of Islamic scholars, and finally to Newton's formalization. The understanding of motion and force evolved across cultures and time. Newton's ability to synthesize these ideas into a precise mathematical relationship marked one of the greatest advancements in science, one that continues to underpin our understanding of the mechanics of the universe. Thank you for watching. Goodbye.